Hi, my name is Amir Salari, and I'm a postdoc at the Department of Earth and Environmental Sciences at the University of Michigan. In this project, we've looked at the coseismic excitation of tsunamis from large megathrust earthquakes in Oaxaca in a tectonic back arc basin that is the Gulf of Mexico, as I'm showing in this movie introduction slide. Here, maximum tsunami wave heights from jacked up CMT earthquakes in Oaxaca are shown in the Gulf of Mexico. I'm going to get back to this movie later on in the talk. The motivation for all of this was this past June's magnitude 7.4 earthquakes in Oaxaca. It created a sort of a mild tsunami in the Pacific Ocean, as I'm showing here in this simulation. There are all kinds of interesting stuff going on here in the forearc. It was the tsunami was picked mostly by local tide gauges along the coast of Central America, and probably one dart buoy in the Pacific, but that was it. Now, if you look closely, there's also this sort of a longer period signal going around in the back arc basin that is the Gulf of Mexico. Could it be real? I mean, what business does it have here in the back arc? In order to look at this more systematically, we looked at the data from the tide gauges all around the Gulf of Mexico to see actually if the data supports this sort of model. The tide gauges all around the Gulf of Mexico here are shown with this black dots, and the single square here in the middle shows the single dart station in the Gulf of Mexico. None of these things have recorded anything. Again, if you look at a signal, it's very, very small. It's millimetric in our simulations, or if not smaller, and it was well below the detection threshold of all of these instruments. But there was this one suspicious signal in Calcasieu, Louisiana, which is exactly on the antipodal side of the sort of a back of the rupture in the back arc, and it was again on the antipodal side of the Gulf. Now, if you look at the data, I'm showing it here in blue. The red curve, as is customary in this sort of business, is the 5-minute smooth version of the signal, and the green curve is the simulation, which I've sort of recorded in the movie that I just showed you, with a sort of a virtual gauge at Calcasieu, Louisiana. And again, if you look at this. The data that I'm showing here, that arrival time kind of matches. So does the period almost. The amplitude doesn't really. But again, the kind of a nominal match that you can see here is interesting. Well, granted that it could very well be due to a million reasons. It could be very well a coincidence. But again, the question that bears attention is, well, what about this arrival time and period match? Now, before you ask me, you can say, well, this is a back arc. What business do we have looking at a back arc from this tsunami? Has these things ever been seen before? And the answer is yes. In the aftermath of the 2011 Tohoku earthquake, there was this kind of a series of waves in the back arc Sea of Japan that was observed by the local fishermen. And of course, it was also picked up by tide gauges all around the Sea of Japan, as was reported by this Pagioff paper by Mordani et al. In 2015. So this is a very well documented, and in fact, so back arc excitation of tsunamis could actually happen. Mind you, the recording of the tsunami signal by these dark tide gauges all around the Sea of Japan was matched the origin time of the earthquake. So before I continue, just a quick word about how we do these things in the tsunami business. Well, in order to look at a tsunami, we need a source. The source is usually considered to be this sort of usually vertical deformation at the bottom of the ocean. We assume that it sort of mirrors the deformation that's going to happen at the surface of the ocean at time t equals 0, and then it's gravitationally unstable. It has to move around, and the result are tsunami waves. The speed of tsunami waves in oceans are given by this equation, which tells you that the tsunami wave speed is going to depend on the ocean depth at any given point. And in other words, consequently, conservation of momentum will tell you that the shape and height of tsunami waves are also going to be dependent on the ocean, the depth of the ocean. Now, enough of this kind of background. Why is it that we've actually never heard of these things? Well, the answer is partly these things we call finite rupture models we use to model the rupture in the forearc, and they are made and are meant to deal with meant to deal with observations in the forearc. This is an example. This is from the study by Chuck Hammond and back in 2011 for Tehuku. Here I'm showing slip and depth distribution of the faults responsible for the earthquake. I'm showing cross sections of both fields along the black transects here above, and I'm showing the cross sections here at the bottom. If you are brave enough to fit an exponential curve to these to sort of extrapolate what's going on here in the western Japanese coastline, then you can see a very, very small number. If you're ready to buy all of this, I mean, that's one big if, but if you're ready to buy this, there's going to be a very small deformation in the back arc. And at the depth of, mind you, about 60 kilometers. Now you can use fancy algorithms to transfer this sort of a slip distribution into the surface of the ocean. Remember, this is the initial condition of the tsunami propagation that we're going to deal with. And so this is what I get from this map, and then I can calculate the tsunami using tsunami simulation codes. And here I have all kinds of interesting things going on in the fore arc, but nothing in the back arc. But if you zoom into the sort of a lower amplitude parts of the color palette, you can actually see there is a signal in the back arc, but it's very, very small. So what's the way around it? Well, we can easily use sort of a point source, a sort of a double couple, because they're localized and they're finite, and you can estimate the fault dimensions using simple earthquake scaling laws from them. And then, as I'm showing here, you can assume a buried incline fault with a focal mechanism and some slip distribution at some angle, and then you can calculate surface deformations easily, as is customary, as people have been doing forever in the tsunami business in a fore arc. Now, a level of complexity emerges when you put a landmass in between. You are dividing the universe into the fore arc and the back arc. And well, these are the initial conditions for the tsunami simulation. But you can see that there is a problem here. You're dividing the universe into two different chunks, fore arc and the back arc, and these two are not interrelated in terms of tsunami propagation. So in terms of initial deformation, you have two different things with two different, probably different eigenfrequencies. Different eigenfrequencies, different dominant period tells you that they're different signals. So for example, the displaced amount of water here I'm showing here in red in the back arc is going to be responsible for the back arc tsunami, but the fore arc is a completely different story, as you can see. So the coseismic deformation can leak into the back arc if the earthquake is large enough and close enough to the back arc basin. Also, following to that argument, you might wonder, what are the important source parameters? What are the important other parameters that are going to affect the back arc tsunami? And finally, I just mentioned that these two things are two completely different beasts in the fore arc and back arc. Can we actually show this? Well, first thing first about propagation. Again, Kakessu was the only place to record this. Why? Well, you can mimic the bathymetry at the Gulf of Mexico using this simple analogy. You have deep water surrounded by shallower water, everything engulfed by land, and you can simulate the tsunami using ray tracing and hydrodynamic simulations from a sort of a half cylinder as a source to just maintain symmetry. And then you can see there is this little bump in the middle. There are some other things. These are modes of edge waves, and the concave shape of the coastline sort of focusing the energy of the edge waves there. And I can do better. I can put a rectangular source here in the middle. And then again, you can see this is more pronounced now. Now, in order to quantify this concavity thing, we can take a flat ocean by a narrow continental shelf next to a coastline, and I can change the sort of a curvature of the coastline by changing the radius of the geographic circle which it's a part of. And at each step, I can simulate a tsunami from this sort of an elongated rupture that I'm showing here in red. And here on the right, I'm showing maximum tsunami wave heights at each step. The vertical bars here are maximum coastal tsunami amplitudes. And if you look at it, there is this peak in the middle. There are other peaks around it, which are different modes of edge wave. So concavity of the coastline focuses energy in the middle, then sort of a nadir. And again, morphology effect matters. What about the source? Well, the source, you can actually do exact same thing. I can, here in this setup, for example, if you look at the top left panel, I'm putting a source in a fore arc, which here is deeper, and it's separated by a narrow spit of land from the shallower back arc. I can permute over all kinds of source parameters and calculate, again, a static deformation, initial deformations, and I'm showing them here across all of these 6 panels. And I can use my simulation codes to calculate the tsunamis in both back arc and the fore arc. And something interesting happens. In the fore arc, we've known this for like a million years. There is the dominant period, the defining nature of the fore arc tsunami is uniquely given by the fault geometry, fault width. No matter what the angles of the double couple are, doesn't matter. It's going to be a fixed number. But in the back arc, it actually depends on the fault's dip angle, which I'm showing here with the with points in the red curve. And well, if you think about it, it's not surprising because remember, the thing in the back arc that matters is this displaced volume of water, and this is going to be, well, affected by the projection of the surface, the amount of deformation that you can transfer in the back arc. Again, I'm showing with this red wedge here on the surface, this is going to be the surface projection. The amount of displacement on the surface, that's going to depend on the dip angle. And all of this, from all of this, you can predict deformation in the back arc, which I'm showing with this red curve here. Now, both of these things are quadratic functions. They follow very similar trends. They're not exactly the same because tsunami simulation codes are not linear. So the dip angle actually matters a lot. Now, move on to Oaxaca. Here, I'm going to focus on this area. I'm showing with a rectangle. This is the seismicity of the Oaxaca region, color-coded according to depth. Now, I can make a cross-section of this seismicity, as I'm showing here on the right along this black transect. The yellow stars are the epicenters of, or hypercenters of the CMD catalog events for which we have good focal solutions, and they're larger than magnitude 6. Again, all of them are shallow. And if you look closely, there is this sort of a seismic gap in Oaxaca just next to the black star, which is the epicenter of this past June's earthquake. And again, this is like about more than 35 kilometers long. This could very well host a large earthquake. Now I can jack up the magnitude of all of these earthquakes, as I showed you in the introduction slide, and simulate the tsunamis in the back arc. The largest tsunami amplitudes from the majority of these are at this point in the south, in Coatzacoalcos, Mexico, and Calcasieu, Louisiana, in the north. And the largest tsunami amplitudes are from those within this sort of a wide rectangle in Oaxaca. Now, again, can I do this in a more systematic approach? I can take the CMT seismicity in the region. I can see there's a large, nice Benioff zone. The further I move away from the trench, the deeper the events will become. I can use Cliff Froelich's old idea of this ternary diagram to partition the mechanisms of earthquakes into three flavors of strike, slip, normal, and thrust. It looks like a shotgun blast, but then I can remove the deeper events to end up with this, which tells me that the region has a dominant thrust flavor. The strike angles of all of these events are peaked around about 280 degrees, nice. And then they have a cluster, sort of a dip angle around 27 degrees. So if they can join hand, that they can actually make a larger event on the asperity. And I can calculate the dominant mechanism for the region like this, and I can brute force a dip angle of 30 degrees, just jacking up the dip angle to make, remember, the larger tsunami in the back arc basin. Now, in order to make fake earthquakes, I can take this Lab 2 model, take the shallower part, capable of making megathrusts, fill it out with my mechanism, and then simulate the tsunamis in the back arc, as you can see here. I'm showing maximum coastal tsunami amplitudes in the back arc by vertical yellow arrows, and as you can see, as the earthquake moves closer to Oaxaca, I am getting larger and larger amplitudes around Calcasieu and Coatzacoalcos. Finally, about landslides, just to wrap it up, landslides can also happen in the Gulf of Mexico from earthquakes in the back arc. You need three ingredients: slopes. There's plenty of slopes in the Gulf of Mexico. You can calculate peak ground acceleration from the fake earthquakes that I just showed you. There is not much in the Gulf of Mexico, so you might think that there is not enough trigger. What about loose masses? There's a history of landslides in the Gulf of Mexico, and the surface waves can actually contribute to all of this, as was shown recently by a paper by Wen-Yon Fan et al. In 2020. You can calculate the overtones of surface waves in the Gulf of Mexico, as I'm showing here, for example, for a large version of this past June's Oaxaca earthquake. And you can see that the peak of all of these deformations is sort of pointed towards Oaxaca. I'm sorry, towards Calcasieu, Louisiana. So back arc tsunamis can create considerable waves. The magnitude and the dip angle of these tsunamis play the most important role. And again, the ideal place to create these tsunamis is going to be the largest tsunami is going to be the earthquakes in Oaxaca. Thanks for tuning in.